Hello everyone, I am Fabien Bouquillon, a PhD student from the University of Lille and the Polytechnic University of Hauts-de-France, under the direction of Giuseppe Lipari from the University of Lille and Smelnia from the Polytechnic University of Hauts-de-France. Today I will present you our works on improving CRPD analysis for EDF scheduling, trading speed for precision. Let us start with the motivation of this work. Today, modern vehicles are embedding functionalities to enhance driving, such as ADAS, ABS, parking assistance, etc. These functionalities are critical because they need to provide a correct result in a correct time window. Otherwise, a critical failure occurs and may involve the loss of a human life. Also, these vehicles are embedding functionalities to entertainment purpose. There is a pressure to integrate all critical and non-critical functionalities on the same electronic boards to reduce the cost. Thus, these electronic boards need to provide high performance, such as command-on-the-shelf microprocessors. Furthermore, real-time guarantees are also required for the critical functionalities that are embedded in the vehicle. The high performance of the command-on-the-shelf microprocessor are coming from their complex features, such as the cache memories. These memories keep a copy of the accessed data closer to the processor for reducing the delay of future accesses. In this work, we only focus on the L1 instruction cache memory. These memories are also a source of unpredictability, because the contents of a cache memory depends on the past execution of all the functionalities. To understand the challenge of providing real-time guarantees while considering a system with a cache memory, we first need to understand how real-time systems are modeled. A real-time system is composed of a set of tasks. Each task is an infinite succession of jobs and is also characterized with three parameters: Ci, the worst-case execution time between all the jobs of a task, Di, the relative deadline, and Ti, the minimum interval time between two jobs. An example of a real-time system is shown in the figure. It is composed of three jobs of a task to I: J1, J2, and J3, with the blue box representing the execution time of the jobs. As you can see, J1 has an execution time equal to the worst-case execution time of a task. Also, each jobs need to finish their execution before their deadline. For example, job J2 needs to finish before D2, which is equal to A2 plus Di, the relative deadline of a task. Notice that jobs may have their arrival time after the minimum inter-arrival time as J3. The worst-case execution time of a task is computed with a static analysis considering the task alone on the system. This analysis performs a cache analysis to classify each access to the memory as a cache hit or a cache miss. On the figure, you can see an overview of a static analysis. First, on the left part, the code of a task is split in blocks called cache blocks. In a case of direct map cache, a cache line is assigned to each cache blocks. They can be stored only in this line in the cache memory during the task execution. After this step, the analysis builds a CFG of a task presented in the right part of the figure. The code of a task is split into basic blocks, that are blocks of sequential instruction that do not contain any branches or conditions except at the end. These basic blocks are linked with edges that are corresponding to the branches or conditions. In this example, the CFG represents a task with 4 basic blocks, BB1, BB2, BB3, and BB4, with a loop between BB2 and BB3. Using the CFG and the cache classification, the analysis searches the longest execution path from the task entry until its end. However, because the worst-case execution time of a task is computed considering the task executed alone on the system, and the real system containing several tasks, a preempting task can evict useful cache blocks from executed tasks, thus provoking access, considering as cache hit during the worst-case time analysis as a cache miss. This phenomenon is called related preemption delay. On the figure is presented an example of CRPD. The tasks TO1 and TO2 are considered executed for their worst-case execution time. When TO1 preempts TO2, it evicts some of its useful cache blocks. And when TO2 continues its execution, it has to reload these blocks from the main memory and provoking a data miss due to the additional delay. Also, it is hard to define the worst preemption scenario since the arrival time of the jobs of a task is not known exactly. In these figures, 2 scenarios are presented. On the left, there is 2 preemptions, TO2 on TO3 and TO1 on TO2. As you can see, TO1 also evicts blocks of TO3, but only those that have not been evicted by TO2. On the right scenario, TO2 preempts TO3, but it is not preempted by TO1, and TO1 only preempts TO3, but this time may evict more blocks since TO3 may have already reloaded blocks from the preemption by TO2. To estimate the CRPD, we need to add another step in the static analysis. This step lists the useful cache blocks of a task that are cache blocked at a point P, which are in the cache and considered as provoking a cache hit by the static analysis later in the task execution without being evicted. Also, this step lists the ECBs of a task. An ECB is a potential blocks from another task that can be evicted during the task execution. On the figure, you can see different UCB sets. They are corresponding to each basic blocks, an UCB set for each basic blocks. Indeed, the analysis considers each basic blocks as one preemption point. From the literature, the best method to compute the CRPD for EDF scheduling is the combined approach proposed by Lunis and his colleagues. Their approach consists in 3 steps. First, estimate the number of preemptions between each task in a given interval of time. Then, computing one UCB set per task as the union of all the preemption points to reduce the complexity of the analysis. And finally, using the formula to compute the CRPD. However, the formula they propose to compute the upper bound to the number of preemptions and the utilization of only one set of UCB per task are imprecise, thus adding a large pessimism in their analysis. In this work, we propose 2 contributions to reduce this pessimism. First, a better bound for the maximum number of preemptions between tasks under EDF scheduling, and finally, an heuristic to reduce the number of considered UCB sets per task. In this slide, I present the imprecision of the bound of the number of permissions between tasks under EDF scheduling. To have a better understanding, the CRPD analysis for EDF is based on the CRPD analysis for fixed priority. In this later, the bound of permissions on one task by another one is given by the maximum number of permissions that can occur during its response time. The response time of a task is the maximum time between the arrival of one of its jobs and the end of its execution. However, computing the response time under EDF is very complex. Thus, Lennis and his colleagues have proposed to use the relative deadline instead to bound the number of preemptions. The formula they propose do not consider the worst case execution time of a task, but only their period and their relative deadlines. On the figure, we represent two tasks, TOJ and TOI. With the formula from the literature, the task TOI can handle not only one, nor two, but three preemption by the task TOJ. However, as we can see in this example, the task TOI may handle just one preemption by the task TOJ if we consider the execution time of a task. Instead of using the relative deadline, we propose to use the preemption interval. It is corresponding to the interval of time starting from the execution beginning of a job of one task until its end. We propose a formula to compute its maximum length for each task. It is not the EDF response time, since it does not consider the time between the arrival time and the start of a task job. On the figure, we show how we compute the preemption interval length for TOI. At moment 1, the jobs of TOJ and TOI arrive. We consider that TOI starts its execution first and is directly preempted by TOJ. In this example, the preemption interval length of TOI equals its worst case execution time plus the worst case execution time of TOJ and the CRPD of TOJ on TOI. Thus, only one preemption of TOJ on TOI is possible. Using the preemption interval in the previous scenario, bound the number of preemption on TOI with a better precision. The CRPD of a preemption by a task TOJ on the task TOI can be given by the size of a maximum set produced by the intersection of the ECB set of TOJ and the UCB set at a preemption point of a task TOI. However, for some tasks there are too many points to consider. In their method, Lennis and his colleagues use only one set of UCB per task as the union of all the UCB set of a task. Thus, a preemption by TOJ on TOI is bound as the size of the intersection between ECBJ and UCBI. In our paper, we propose an heuristic to fix the maximum number of UCB sets per task that we call M-reduce on the figure, thus providing a trade-off between the accuracy and the complexity of the analysis. Indeed, we do not only use one UCB set per task, as the solution shown at the left of these figures, nor we do not use an UCB set per each preemption point of a task, as the solution at the right of these figures. We now present the result of our contribution with a cache memory of 4 kilobytes, two-way set associative with 12 tasks and a reload time of 200 cycles. The maximum number of UCBs set per task is 4. The baseline curve representing the percentage of schedulable task set with the combined approach according to the workload of a task set is the black one. The purple curves represent the performance of the combined approach using only the preemption interval. The red curves represent the combined approach using only the heuristic to fix the maximum number of UCB sets, and finally, the yellow represents the combined approach with the preemption interval and the heuristic. As you can see, at workload 0.88, the combined approach with the preemption interval and the heuristic classify as schedulable 65% task set over the combined approach unmodified. In this slide, we present the analysis time of our method. Using the preemption interval increased by 0.5 seconds the analysis time for the combined approach for 12 tasks, compared to the analysis time with only the combined approach. Also, using 4 UCB sets as the limit per task increased by 1 second the analysis time of the combined approach. Thus, we can see that the analysis time for our method is reasonable. To conclude, in this work we propose 2 contributions: a better bound to the maximum number of permissions between tasks and an heuristic that provides a trade-off between the precision and the complexity of the analysis. In future works, we'll extend our work to data cache, multi-level caches, and multi-core. Thank you for listening.